Today we're gonna prove the Euclidean algorithm, but if you don't know what it is, or you want a quick recap because you've kind of forgotten, here's the Euclidean algorithm. You start with two integers a and b, then you order the two integers so that a is larger or equal to b, and you let a equals a minus b. If either a equals 0 or b equals 0, then the non-zero value, the GCD of the original is equal to the GCD of the original a and b. So there's actually an improvised version here. So basically what you do is, instead of directly letting a equals a minus b, since there might be various copies of b inside a, you let a equals qb plus r, and then you let a equals a minus qb. So q here is any integer, and the q has to be, positive. So this simplifies the process a lot, because let's say I had GCD 32 and 2. So let's say I had GCD 32 and 2. If I did the original process, which is a equals a minus b, I would have to let 32. So I have to change this to GCD 32, and then 28, 2, and then 24, and then 26, 2, 24, 2, 22, 2, blah, 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 until one of the values of 32 and 2 is 0. So that's an extremely annoying and tedious and, time-consuming process. You don't want to do them in any of your exams or any time you need to use the Euclidean algorithm at all. So we've simplified this. This is basically the quotient and remainder. So Q is quotient, R is remainder. So A is larger than B, right? If I divide A by B, we're going to get an integer Q, and the remainder is going to be R. So remainder R. So let's say I have 32 and 2. 32 divided by 2 is going to be 16, and there's no remainder. So basically we'll let A equals a minus qb. So we'll let 32 equals 32 minus 16 times 2. So we'll let a equals 32 minus 2 times 16, because q is 16 and b is 2. And basically we'll directly get 0. So GCD 32, 2 is GCD 2, 0. So the GCD of 32 and 2 is going to be 2. So that simplifies the process a lot compared to our previous method. So now let's prove the Euclidean algorithm. So firstly, we have to state a few things. So let's assume we start off with GCD AB. A is larger or equal to B. And they're both, positive. So let's say A equals QB plus R. We're gonna believe that the GCD of A and B is equal to the GCD of B and R. So why is this? Let's say both A and D are divisible by, the factor, let's say, k. So both A is divisible by k, and B is divisible by k. Then this means that for any integer q, basically k is divisible by qb. So basically, why is this? B already has whatever factor K needs to be, so B already has K times another integer. Let's say it's called D, so B already equals K times D, right? If we multiply both sides by Q, we get QB equals K times D times Q. This is obviously still divisible by K because it has a factor of K in it. So K is divisible by QB, and we know that K is divisible, so based on these two, we know that K is divisible by A minus QB. So once again, why is that? Let's say A equals K times D, and then QB is equal to Q times K times H. So if we do A minus QB, well, then we'll get K times D minus Q times K times H. And that is equal to, so if we factor the K out, that's D minus QH. So we still have a factor of K here, and we assume that D minus QH is larger or equal to 0. So basically what we get is that A minus QB is also divisible by K. So since A minus QB is divisible by K, and here, so if you scroll back up, we've assumed that A equals QB plus R. So A equals QB plus R. If we rewrite that equation, we get R equals A minus QB. So basically, we end up with, so this here, K is divisible by, so A minus QB is divisible by K. It's basically R is divisible by K. Since R is divisible by K, and also the fact that both QA and QB are divisible by K, we can assume that, so we can let A equals K times D, B equals K times E, and R equals K times F. Since they're all divisible by K, there's factors of K inside them, inside the integers. And D, E, and F are all integers. They're at least 1, so they're positive integers. So basically, we know the GCD of K times D, that's A. We know that we want to figure out the GCD of K times D and K times E. And let's assume D and E are both like prime factors of each other. So the common GCD of the greatest divisor of D and E are 1. So the GCD K times D and K times E, when D and E cannot divide each other, is going to be K. And then GCD K times E and K times F, in the circumstance that E and F also cannot divide each other, is also going to be equal to K. So the GCD of A and B is equal to the GCD of B and R. So you might be asking, well, how do we know if D and E are like not prime? We'll do that another time, but for now, this is the proof. So thanks for watching. Remember to like, subscribe, and also comment below. If you don't like my videos, please comment below for the reason why. And please share them with your family and friends. Bye. I hope you learned something useful today.